Hi, this is Mr. Swanson, and today we're going to look at the first lesson in our chemical reaction unit called Balancing Chemical Reactions. I highly recommend you following along on your own set of notes, but trying some of the practice problems and pause the video when you need to. So before we get into the balancing, let's talk about some of the basics involving chemical reactions and some of the terminology so we have a shared vocabulary. So when we use a word, we all understand what we're saying. So a definition, and when I say a definition, there's many different ways to say this, but it's a process where one thing is converted into a different thing. And so you could say molecules or you could say compounds, and there's variations on this definition, but converting from one substance into a different one, not just a phase change, which might be like a physical change. Now, to see if a chemical reaction actually happened, you're going to see different, if you to observe a reaction, you're going to see changes in maybe color. You're going to see changes in smell. You might see a phase change. So, right, phase change. You can see some heat. Okay, bubbles, gas. These are some of the different some of the different pieces of evidence that you could see for a chemical reaction. There are a couple more important terms that you need to be aware of, and the first one is reactants. So reactants are like the ingredients of the chemical reaction, and you're going to find them on the left side of the chemical equation. So right there. And they're what's present at the start. And like I said, they're the ingredient. It's what you're going to be mixing together or something like that. And the products are over on the right side. And they're what is present at the end of the reaction. And you can, like the word products, it's what's produced. Okay, so different words can describe those, but you want to think about the ingredients versus what is made. Now, sometimes there's other things called catalysts, which are not part of anything that's being changed, but what they do is they help speed up the reaction. So in a later unit, you might learn about how fast a reaction happens, and sometimes they happen very slowly. And so for efficiency's sake, we put in catalysts that are not really part of the reaction, but they just help speed it up, or they help activate it and start it. And so sometimes you might put the catalyst up here over the reaction arrow, showing that it's not really part of the reaction, but it helps speed it up. Now, the other word is a coefficient. So a coefficient is the number in front of the reaction. And let me change colors here so you can see the coefficient is a 2 here and a 2 here. And if there's no coefficients, you would assume it's a 1. So there's a 1 right there. And what these coefficients tell you is how many of the molecules there are, or how many of the compounds there are. So this one says that there's 2 hydrogen peroxide molecules and 2 water molecules and 1 oxygen molecule. But the subscripts, and I'll choose a different color, the subscripts are what are below. Remember, sub meaning below. And so the subscripts tell you right there how many of each of the atoms. And again, if there's no subscripts, you assume 1. So how many atoms there are. Okay, so you want to pay attention to that. And so you're going to see here that there's, in 1 molecule of hydrogen peroxide, there's 2 hydrogen atoms. And so in 2 molecules, there's a total of 4 hydrogen atoms. And so that's what we're really going to be paying attention to using these coefficients and subscripts. Now, we want you to be aware of it, that we're going to teach you the basics of chemical reactions, but there's a few more things you might want to pay attention to, or that you might see when, looking at something online or reading an article. And the first one is the direction of what the reaction is going to happen. So the arrow means like yields, or it means that there's a chemical reaction, and it shows you which way it's going to go. some reactions can actually go backwards, and so we can use, or they can go both ways, and so we use that double arrow showing that it's reversible. It can go backwards. Now we use little parentheses, and you're going to see them after, like if I write H2O, you're going to see like a little S, and that means solid. So we're talking ice right there. So we put that kind of down as a subscript after the molecule to say what state of matter is it in. So these are common. These right here are all states of matter. Aqueous means dissolved in water, which most things are for a reaction to happen. And then these last 5 are kind of the conditions of the reaction. So they're not in a reactant or a product. They're not actually an ingredient or something that's made, but it's like the temperature. So here's a specific pressure it's at, or this is just saying it's a high pressure, and this is saying what temperature it's happening. Here is a catalyst, so we put that over the arrow, or here we need to heat it. So sometimes above the chemical reaction, we say the conditions. So something like heat might break down water into H2 plus O2. So you're going to see other symbols, and it's important that you can, refer back to this to see what we're talking about. Now, the topic that we are studying is called balancing chemical reactions, and why we have to focus on that topic is because of the law of conservation of mass. And again, there's many ways to say this, but you can't create or destroy mass, and so it can only get converted from one form to another. And so what does it have to do with chemistry? Well, in a chemical reaction, and so I'm going to abbreviate reaction from now on Rxn, so that's reaction. It obeys this. And so what that means is whatever the mass at the start of the reaction, let's say there's 18 grams of stuff, in the end, there's going to be 18 grams of stuff. Now, it might be in a different form, and it will be in a different form, but this chemical reaction definitely obeys this. So you're just going to have different substances. Now, when you do a chemical reaction, you might start with 18 grams, but you only weigh 16 grams on a scale. And you're like, well, what happened? Well, there was maybe about another 2 grams of some kind of like gas that escaped. And so you're not measuring it, but it's there. You can be completely sure of the fact that if you start with 18 grams, you're going to end with 18 grams. You just might have to find that. Now, how do we kind of show this conservation of mass is by showing the balanced chemical equation. And take a second to read through these rules. And just like a game that you might play, you can read through the rules at the beginning, and it's super important. But doing some of the practices can help give some perspective on the rules. So what we're going to be doing is counting to make sure we have the same number of atoms on each side of the chemical reactions. And here are some hints at kind of how to do this. And until you become a master in chemistry, or until you get your degree in chemistry, we want to go through these steps every single time, because it's what's going to make sure your answers are correct. All right, the second step that we just saw said to make sure you have counted the atoms on each side and to make sure they're the same. And so to do that, you just want to read through the molecule. So this is like one molecule or compound, however you want to say it, depending on what it is. And you're looking at the subscripts. And so here I don't see a subscript. And so when there's no subscript, we know there's one of them. So there's one Na, and then I look and I see there's 2 carbon and 3 hydrogen, and there's 2 oxygen. So you're just looking at these subscripts. Now, in the second example right here, we see we have 5 of this whole thing. Okay, so when I see, again, no subscripts for zinc, I normally would assume that's 1, but since there's 5 of them, that means there's 5 zinc. And again, I would assume there's 1 sulfur, but since there's 5 of the whole molecules, there's 5 sulfurs. And then here, the trickier part is in 1 molecule, there's 4 oxygen. And so in 5 molecules, there's going to be 20 oxygen atoms. Okay, so it's just a little bit different. And then finally, the third example, This 2 kind of follows the mathematical kind of distributive property. So this 2 applies to both the O and the H. So when we're looking at this, there's only one Mg because that 2 doesn't apply to that. But there's 2 oxygens and 2 hydrogens. So you want to pay attention to the subscript and treat everything on the inside of those parentheses like that. So why don't you take a second to count up and write down how many of each type of atom are in both of these examples. And again, we're trying to show all of those different kind of difficulties in this problem. So take a second to do it, and then check your answers when you're done. So check your answers. Did you get what I get right here? And if not, see if you can follow kind of the arrows and how I distributed those numbers kind of outside of the parentheses or those coefficients at the front. All right, so now let's get a little bit farther into balancing a chemical reaction. And so I have right here a chemical reaction that's super important, one that Matt Damon actually made very famous in the movie The Martian, where he was trying to make water for his plants, and he knew you could do that using hydrogen and oxygen. And this is a very important reaction for space travel because we need water, of course. Now, what happened was he ended up blowing himself up. He wasn't using the exact right proportions, and we can see that right here, that on the left side of the equation, we have 2 hydrogens and 2 oxygens as our reactants. But as a product, we have 2 hydrogens and only 1 oxygen. And so this does not obey, this does not obey the conservation of mass. So that, I'm going to abbreviate that, conservation of mass. And so what we have to do is we have to change this. We have to change the proportion and the ratio to make sure this shows the conservation of mass. And so what we're going to be doing is we are going to be adding coefficients in front of this to say, okay, no, I need 2 hydrogen molecules and 1 oxygen molecule to produce 2 water molecules. And this is going to then, now it's okay. So now we don't violate the conservation of mass. And so that's what we're going to be doing when we say we're balancing chemical reactions. Now, balancing chemical equations, for some people, is kind of fun because it's a little bit of game, and some people intuitively see it, and some people kind of need to follow through kind of a process. And so we can give you some tips and tricks, but what I can tell you is we're only going to give you chemical reactions that can be balanced. So if you know that it can work, you're just going to have to kind of play around with it and try it until you get it right. And so it's just kind of like a puzzle. You know, you can start with the corners, you can start with the middle or the outside, but there's a way to make it happen. You just have to play around with it until it works. So see right now, if you can just kind of intuitively see what coefficients are you going to have to add to make sure you have equal number of each type of atom on each side. And so why don't you try for right now to see if you can figure out what that is. And some of the tricks are keeping the things that are by themselves last. So often that's hydrogen and oxygen. So why don't you pause this and see if you can figure it out, and then come back for the correct answers. So hopefully you got these answers or similar answers to this. And I would say that these are easy ones. These are ones where when you added a coefficient, it only changed kind of one thing at a time. And so most of you probably were able to kind of see these numbers happen. Now, that's not how we really want you to do them, because they won't always be this easy. So we're going to teach you kind of some of the steps on how to kind of guarantee that you're going to get the correct answers. So if this didn't make sense right now, hold on for a little bit and we'll kind of clear it up. Here's an example of a combustion reaction. And so we want to give you another tip, which is you can see oxygen is in 2 different compounds. It's in 2 different molecules on the right side. And so that's the one we're going to save for the end, because it's going to be the one that's kind of the hardest. And so try to see kind of what you can do with this one to see if you can figure out the coefficients, and then you can kind of come back for the answers using the hint of keeping the oxygen for the very end. All right, so here's the answers, and again, we don't write the coefficient of 1 just because it's assumed. And so here you see at the very bottom, carbon and hydrogen was pretty easy to figure out, but you had to add up the oxygen from both molecules to figure out that there was 10 of them, and so then you had to adjust it on the left side as well to make 5 O2 molecules. And so that's why we say save hydrogen and oxygen often for the end, because they're found in the most molecules. Another tip that you want to employ is when the polyatomic ion is whole in both sides, and I'll show you what that means. When SO4 is as SO4 and it's not broken down into sulfur and oxygen, when you see it like this, you want to treat it as a whole, okay? And so you can see that there's 3 of that SO4 molecule right there, so you can instantly put a 3 kind of right here, because then it's balanced. That changes the number of hydrogens, so now we have 6 here. So I can put a 3 over here, and now I have 6 hydrogens on that right side. And then finally, I just have to account for my aluminum, and I have to put a 2 here. Now this is just a lot easier to think about than saying, okay, now I have 12 oxygens on the right side. How do I get 12 on the left side? So treat them as a whole if they are present as a polyatomic ion on both sides of the equation. Now hopefully you were able to see kind of those rules and how they play out, but we're going to get to equations that are a little bit more challenging, and so you're going to have to show your record. Now, most of you have probably never balanced a checkbook, but what we're doing is we're accounting for all of our expenditures. We're accounting for all the different atoms, and so you want to do some kind of T-chart or some kind of, I used to call this a T-chart, because I did it a little bit different than this. So you want to keep track of your elements on the reactant side and elements on the product side, and they have to be the same thing. So if you have 4 of an element on the left side, you have to have 4 of it on the right side. And so let's kind of go through and keep a tally, no erasing. This is really important to not erase things. You just want to maybe put a line through it to watch how I kind of balance this chemical reaction. So let me first move this real quickly. Well, I don't need to move it. So, okay, so you first want to start by counting up how many of each type of element are on each side. So there's 1 phosphorus here, there's 5 chlorine, there's 2 hydrogen, and there's 1 oxygen. Okay, good. And then there's 1 phosphorus here, there's 1 chlorine, there's 1 plus 3, so there's a total of 4 hydrogen, and there are 4 oxygen. Okay, and so what we do right now is we can say, all right, and let me just get this out of the way because it's distracting to me, but what we want to do is say, okay, we got to pick one where it's not balanced, and we got to try to balance it. And often in this example, there's not one right way to start. I often start with the biggest difference. So obviously the phosphoruses are equal, so that's good, but the chlorines are not. So I'm going to start by saying, okay, if I have 5 chlorines on the left side and I only have 1 here, then I want to add a 5 right here. Now to do that, what I want to do now is, okay, that changes my chlorine to a 5, but it also changes my hydrogen now to a 9. Yeah, so that made a change. It changed 2 things. Now, you would keep following this process, but this reaction is actually a little bit more difficult than I want to do to kind of start off with. So we're going to take this idea of keeping a tally for your atoms, and we're going to go on to another problem, which is a little bit easier to solve. Now, here, again, you're going to want to keep a tally, and in this time, because we see this polyatomic ion on both sides, we can treat it as one thing, and so that's why you see it down here as one thing. So give it a try on your own to see if you can count up how many of each type of atom, and come back and I'll help you balance it. So hopefully you counted the atoms correctly and you have these numbers. So, where do you go from here? Well, like I said, again, I often take the biggest difference. So 3 and 1 is the biggest difference, or just the top one is fine to start with. So, and as you get better, you'll kind of see where an obvious place to start is. But for now, let's just go with this top. So I see 3 NAs on the left side and only 1 on the right side. So I'm going to put a 3 here as a coefficient. Again, I'm not going to erase it. That changes that to a 3. And that also changes that to a 3. So our sodiums for now are balanced. Over here, though, now we only have 1 phosphate on the left side and 2 on the right side. So I need to put a 2 here. And that changes the phosphates to a 2. But now, again, it changes the sodiums to a 6. So you're going to often kind of get something balanced, but you're going to have to make a move to unbalance it. Just kind of like how, I don't know, in chess, you have to sometimes sacrifice something to kind of get towards the end. This is what you're doing. You're having to make a second move. So again, at this point, we could go back and rebalance the sodium. Okay, so now I have 6 sodiums on the left side. All right, so I'm going to have to put a new number up at the top. Let's try 6 of them. Okay. So now we're going to go down to our calciums. So there's 3 calciums on the left side, or on the right side, and 1 on the left. So a simple 3 right here can fix that. And that also made there 6 chlorines, and so everything is balanced. So the coefficients to balance this are 2, 3, 1, and 6. So that's often in a multiple choice problem. You might say, like, what are the coefficients going to be when the equation is balanced? And you would see kind of the answer is 2, 3, 1, and 6. So here's another problem where things get a little bit messy, and you definitely want to keep track of your atoms. So if we look on the left side, we see 1 nitrogen and 3 hydrogens and 2 oxygens. And over here, we see 1 and 2 and 2. Okay, and so right away we can see we have 3 hydrogens and 2 hydrogens, and so 3 and 2 are factors of what number? 6. And so right away I know I'm going to have to get 6 hydrogens on each side. So if I put a 2 right here, that makes it 6 hydrogens and 2 nitrogens. And over here, I'm going to have to put a 3 to get to 6. So that gives me 6 of these, but it also gives me 3 oxygen. Okay. All right, now the nitrogen's not balanced, so if I put a 2 here, right there, but now it changes, so I have a total of 5 oxygen. Okay, and again, 5 and 2 aren't balanced, and so 5 and 2 go into what number? Okay, well, 10. So now let's go back and change this. We need to get to 10 oxygen. So 5 is going to go here, and that gets me to 10 on the left side, but how are we going to get to 10 on the right side? And so there's, a couple different ways we can do that. But one thing we have to do is we have to make this number an even number. And so let's put a 6, let's make it a 6 here. And so if we make it a 6 here, that gets us 12 hydrogens and a total of 8 oxygens. Now, that still doesn't work, so let's make this a 4. So that has a total of 10 oxygens, but it has 4 nitrogens. Well, if we put a 4 over here, our nitrogens are a 4, our hydrogens are a 12, and our oxygens are balanced to be 10. 5 times 2. So here the coefficients are 4, 5, 4, and 6. And again, this one was definitely, I would say, a hard one. So if this didn't, if you're just learning balancing right now, and then this one didn't make sense, it's understandable. This one was a little bit difficult, and you had to sometimes undo something, but their answer is always doable. And you just have to keep changing one thing and keep track of your atoms. So try to use all of the tips and tricks that you've seen, as well as just keeping track of the atoms, and try to solve these. And pause it right now and come back for the answers in just a little bit. All right, as I'm solving it, I forgot to tell you there's one more tip that we can say is if you get to a point where you have kind of odd numbers and even numbers and they're not going to balance out nicely, like right here you have 9 oxygen, so that's going to make it hard to balance with an even number over here. What you can do is multiply everything by 2 and then kind of start over. So what we're going to do is we're going to put a 2 here and a 2 here, and we're going to make this 16, and we're going to make this 18. And combustion reactions are notorious for being tedious to balance, and then kind of readjust everything. And so now there's 16 carbons, there's 36 hydrogens, there's 4 oxygens. Again, like I said, this seems like it's going to be difficult, but it's going to work out pretty nicely. 16 carbons, hydrogens, there's 36. And now I have 18 oxygens plus 32, so total of 50 oxygens. And so all I have to do now is make the bottom number match. And so I can do that by just changing this to a 25. And so when I multiplied everything by 2, that allowed this to kind of keep going further. Now, I make my T-charts like this also, so you can see people do it like this. It's just kind of simpler, what people prefer. You have the reactants and then the products. So pause it again and keep working on that, but I would use that multiplying it by 2 trick. Okay, so hopefully you are able to follow kind of my work and see how these are the correct answers. And if not, definitely go back and look at your T-chart because you probably did something wrong in the T-chart. So practice is going to really help for this skill. But if you find yourself still struggling, go back and kind of read through some of those tips and tricks, and maybe you're kind of forgetting one of them.